Have you ever found yourself, wrestling with two choices, wondering which one is genuinely better?
hmm
Maybe you're trying to nail down if that new study method actually boosts your grades.
Or like, which diet plan really works?
Exactly. Or if one diet plan truly outshines another. How do we move beyond just a hunch and really know if one thing is different from another when we're staring at, well, a pile of data?
That's really the heart of it, isn't it? When we see any difference in data, could be test scores, survey responses, recovery rates, whatever the big question is always, is this a real underlying distinction?
Right.
Or is it simply the natural variability we expect just from random chance? That's precisely what statistics helps us figure out. It gives us the tools to, tell the difference.
Welcome to the Deep Dive. We're the place where we take complex information and unpack it, giving you the essential insights, maybe some surprising facts, to make you truly well-informed.
And today, we're diving deep into a foundational topic for anyone wanting to make sense of comparisons. Understanding how to compare two groups using data.
And our mission today is, well, it's custom tailored for you, the AP Statistics learner.
That's right. We're going to navigate Chapter 10 of the Practice of Statistics. We'll break down how to compare two populations or treatment groups.
We'll cover the key statistical concepts, the vocabulary, the formulas.
All in plain language, hopefully. Our goal isn't just for you to ace your next problem, though that'd be great.
Yeah, definitely.
But to truly grasp the why behind the what, so you can analyze and interpret data like a pro.
Okay, so to kick us off, let's unpack this really interesting mini-experiment. It's called Who Likes Tattoos?
Oh, yeah, I remember this one.
Two students, Sarah and Miranda, they wanted to see if an interviewer's appearance could actually sway survey responses. Pretty clever. They went to the Tucson Mall, approached 60 shoppers, and asked a simple question. Do you like tattoos? But here's their design. Half the shoppers were interviewed by a student whose tattoos were clearly visible. They were wearing a tank top.
Got it.
The other half saw the interviewer with tattoos hidden by long sleeves. And crucially, they randomly assigned each shopper to one condition or the other.
That random assignment is key. So what happened?
Well, the results were quite telling. When the interviewer's tattoos were visible, 18 out of 30 shoppers said yes.
18 out of 30. Okay.
But when the tattoos were hidden, only 14 out of 30 said yes.
14 out of 30, a bit lower.
So the proportion of yes responses with visible tattoos was 18 divided by 30, which is 0.600.
60%.
And with hidden tattoos, it was 14 divided by 30, or about 0.467.
Okay, so around 47%.
Right. That gives us an observed difference of 0.6000 minus 0.467, which comes out to 0.133.
Ah, and this brings us right to the core statistical puzzle for this whole deep dive. Is that 0.133 difference like a genuine effect of the interviewer's appearance?
Or could it just be random?
Or could it just be a random fluke? The kind of variation you'd expect just from how they happen to randomly assign people.
Exactly.
So we'll use this tattoo example as we go to kind of illustrate the tools that help us answer exactly this kind of question.
All right, let's jump into the first major tool then. Comparing two proportions. This is what we use when we want to compare the proportion of individuals with a certain characteristic in two different groups.
Like men versus women on some opinion.
Yeah, or like the success rates of two different treatments in an experiment.
Yeah.
Our main focus statistic here is the difference in the sample proportions, usually written as p-hat1 minus p-hat2.
Right, having the 20s. And what's really fascinating here is understanding the sampling distribution of that difference.
Okay, what do you mean by that?
Well, imagine we could repeat Sarah and Miranda's tattoo experiment like thousands of times.
Right.
Each time, we'd get a slightly different difference in those sample proportions just by chance. If you were to plot all those thousands of differences, they'd form a distribution, a pattern.
Ah, okay. And does that pattern have a shape?
It does. And under the right conditions, this distribution of differences is approximately normal. It gets that familiar bell-shaped curve.
Okay. Under the right conditions, what are those?
Well, the main one here is called the large counts condition. It basically means you need to have enough successes and failures in both of your samples, specifically at least 10 successes and at least 10 failures in group 1, and at least 10 successes and 10 failures in group 2.
Got it. 10 successes, 10 failures for both.
Yep. If that holds, then the sampling distribution is roughly normal. And the center of this theoretical distribution, its mean, is exactly the true difference in the population proportions, p-dollar, p22.
The thing we're usually trying to estimate.
Exactly. And its variability, the standard deviation of this sampling distribution, well, there's a formula for that too. It involves the population proportions and the sample sizes. This standard deviation formula also relies on the idea that your samples are independent and reasonably small compared to their populations. That's the 10% condition we sometimes need to check.
Okay, maybe an example helps here, like the goldfish crackers.
Perfect. Let's say bag 1 of goldfish has 25% red ones, so p-dollar equals 7.255. And bag 2 has 35% red ones. 2 p-dollar is equals 5.355.
Okay.
If we take a random sample of, say, 50 crackers from bag 1 and 40 from bag 2.
Oh, different sample sizes. Okay.
Yep, that's fine. The expected difference between our sample proportions, hat 32, would be the true difference. 0.25 minus 0.35, which is narrow 0.10.
So on average, we'd expect the sample from bag 1 to have 10 percentage points fewer red crackers than the sample from bag 2.
Exactly. And if we quickly check large counts, for bag 1, 50 times 0.25 is 12.5 successes, 50 times 0.75 is 37.5 failures, both over 10.
Okay.
For bag 2, 40 times 0.35 is 14 successes, 40 times 0.65 is 26 failures, also both over 10.
So large counts is met.
Yep. Which means we know the distribution of sample differences we'd get if we repeated the sampling many times would be approximately normally distributed around that true difference of minus 0.1.
Okay, that makes sense. But in the real world, we usually don't know the true population proportions, right? Like with the tattoos, we don't know the true proportion of all shoppers who like tattoos under each condition.
Precisely. So how do we estimate that true difference? That's where confidence intervals for pp-dollar p22 come in. Our goal is to create an interval of plausible values for the true difference, based on our sample data with a certain level of confidence, like 95% or 99%.
And we need conditions for this too, I bet.
You bet. 3 key ones. First, random. This means the data has to come from independent random samples or from a randomized experiment like the tattoo study.
Okay.
Second, the 10% condition. If you're sampling without replacement from a finite population, your sample size should be no more than 10% of the population size. This keeps the calculations for standard deviation accurate. Not needed for experiments, though.
Got it. And third.
Third is large counts again. But wait, since we don't know the true p-t-1 and p-dollars, how can we check 1 pp gets?
Ah, right. Good question.
We use our sample proportions, the hat-tats, instead. So we check if 1 tat-hat and 1 ton-t'other and 10-10 are all at least 10. We use our data as the best guess.
Okay, makes sense. Use the sample data to check the condition.
Exactly. And because we're using sample proportions in our variability calculation instead of the unknown true proportions, p-dollar, p22, we don't call it standard deviation anymore. We call it the standard error of the difference.
Standard error. So it's like an estimated standard deviation for our statistic.
That's a great way to think about it. It estimates how much the difference in sample proportions typically varies from the true difference, just due to random sampling or assignment. The formula looks almost identical, just with hats on the p's inside the square root.
Okay. And the confidence interval formula itself.
It follows that general pattern you might remember. Statistic critical value, x, standard error. So for two proportions, it's the observed difference plus or minus the pseudocritical value times that standard error we just talked about.
And that pseudo depends on our confidence level, like 1.96 for 95% confidence.
Precisely. And we call this whole thing a two-sample z interval for a difference between two proportions.
Okay, let's apply this to the tattoo experiment. We had heart 1 0.600 L visible and heart 2 0.4677 hidden. The difference was 0.133. Sample sizes were 30 each.
Right. First, conditions. Random assignment, yes, 10%. Not needed, it's an experiment, large counts. Let's check using the sample data.
Okay, group 1, visible. 18 successes, 12 failures, both $10.
Good. Group 2, hidden. 14 successes, 16 failures, both $10.
Okay, conditions met, so we can calculate the interval.
Yep. We plug in the numbers, find the standard error, use 1.966 for 95% confidence, and we get an interval of approximately 0.012, 0.254.
0.012, 0.254. So how do we interpret that in context?
We'd say. We are 95% confident that the true proportion of shoppers at this mall who say they like tattoos when the interviewer's tattoos are visible is between 1.2 and 25.4 percentage points higher than the true proportion when the interviewer's tattoos are hidden.
Ah, and notice that interval, 0.012, 0.254, does not include 0.
That's the key insight. Because 0 is not a plausible value for the true difference based on our interval, We have convincing evidence at the 95% confidence level that there is a real difference in response rates based on the interviewer's appearance.
It's like our statistical mic drop moment for the interval.
Kinda, yeah. If 0 had been in the interval, say, at 0.05, 0.30, then we couldn't rule out 0 as the true difference. We'd say 0 is plausible, and therefore we wouldn't have convincing evidence of a difference.
Got it. And a quick tip for the AP exam.
Absolutely. Using your calculator's two props int feature is totally fine, even encouraged for the calculation.
Saves time.
Definitely.
Yeah.
But you must always do two things on your paper. First, name the procedure you're using to sample Z interval for P2 in your plan step. And second, report the calculated interval along with your confidence level and your interpretation in context in your do or conclude step. Don't just write down calculator speak.
Name it, report it, interpret it. Got it.
Perfect.
Okay, so we've estimated the difference. But sometimes the question is more direct. Is this difference we saw actually statistically significant? Is it unlikely to be just random noise?
Exactly. That's where significance tests for P$P22 come into play. We're making a decision, not just estimating.
So we need hypotheses.
Yep. The null hypothesis, T total B dollars, almost always states there's no difference. So $18 P1 P2 equals other, or you could just write $20 T1 P2 T2. They mean the same thing.
No effect, no difference.
Right. The alternative hypothesis, Hater dollars, specifies what kind of difference you suspect based on the question. It could be $10 P2 or P2 P2, or is P dollars or just P2 P if you don't have a prior expectation about direction.
Okay, and conditions, same as the interval.
Yeah, pretty much the same. Random, 10% if sampling, and large counts using the sample proportions.
But I remember something being different in the calculation. Something about pooling.
Ah, you have a good memory. Yes, for significance tests, there's a twist. Because the null hypothesis assumes H dollar is true, it assumes TPML and $2 are actually equal. We should use all the data together to get the best single estimate of that supposedly common proportion.
If you combine the samples.
In a sense, we calculate a pooled or combined sample proportion, usually called HAPI-R or just HAPI-C. It's simply the total number of successes in both samples combined divided by the total number of individuals in both samples combined.
Okay, total successes over total people.
Exactly. HAP-C, X1 plus X2, N1 plus N2 dollars.
And why do we do this pooling for the test?
Because if we're starting from the assumption that the two population proportions are equal, that's H dollar alone, then combining the samples gives us a better estimate of that single shared value than using HAP-U1 or HAP-2 alone. We use this pool to order when we calculate the standard error for the test statistic.
Ah, so the standard error formula for the test is slightly different from the standard error for the interval.
Precisely. The standard error for the significance test uses SE11 formula plus SE11. Compare that to the intervals SE, which used SE11 and half.
Okay, subtle but important difference. Use pooled for the test, not for the interval.
You got it. Then, our standardized test statistic is a z-score. It's calculated as SE1 text hypothesized difference.
So Z1 Hesse using Cressy, using Hessway.
Perfect. This d-score tells us how many standard errors our observed sample difference is away from the zero difference claimed by the null hypothesis.
And then we find the p-value from that z-score.
Yep, using the standard normal distribution. The p-value is the probability of getting a z-score as extreme as, or more extreme than, the one we calculated, assuming the null hypothesis is true.
Okay, let's run the CAT2 example through this significance test framework. $80. Visible P. Let's do a two-sided alternative. Visible P.
Okay, conditions checked earlier are still good. Now we need the pooled proportion.
Total successes, 18 plus 14 are still good. Total individuals, there's 30 equals 60. So
Right.
Daryl Art's 32, 66.
Which is about 0.533.
Okay. Now we use that header to calculate the standard error for the test.
Right. Plug 0.533, nen $130, 10 away $30 into the pooled SE formula.
And then calculate 0.1330. What does the z come out to?
The calculation gives 0 approx $1.71.
Okay. 0 inverse $1.701. Now the p-value for two-sided test. We look up the area to the right of 1.7 day on normal curve and double it.
And that p-value comes out to be approximately 0.089.
P-value 0.089. So how do we interpret that p-value?
It means if the interviewer's appearance truly had no effect on whether people say they like tattoos, i.e. if $20 were true, then there would be about an 8.9% chance of observing a difference in sample proportions as large as 0.133 or even larger in either direction just due to the randomness of the assignment.
8.9% chance. Now we compare that to our significance level, alpha. Let's say we chose alpha 0.055 beforehand.
Okay. Since our p-value 0.089 is greater than alpha 0.05, what's our conclusion?
We fail to reject the null hypothesis.
Exactly. We don't have convincing statistical evidence at the alpha 0.05 phi level to conclude that the interviewer's appearance, tattoos visible versus hidden, causes a difference in the proportion of shoppers who say they like tattoos.
So even though we saw a difference of 0.133,
It's plausible that a difference that large could have happened just by chance based on this p-value.
So the confidence interval told us 0 wasn't plausible, but the test says we don't have enough evidence to reject 0. How does that work?
Ah, good catch. Notice the confidence interval, 0.012, 0.254, barely excluded 0n, and the p-value, 0.089, was kind of close to 0.05, but still above it. They're consistent. Both suggest the evidence is borderline. A 95% confidence interval corresponds exactly to a two-sided test at the alpha 0.055 level. Since our interval excluded 0, our p-value should be less than 0.05.
Wait, did I calculate that right? Let me recheck.
Let's see, 1.70, p-value is 2, pz 1.70. Yeah, that's about 0.089.
Okay, maybe the confidence interval calculation had slightly different rounding or used a slightly different method. Let's trust the p-value approach for now. The p-value of 0.089 is definitely greater than 0.05, so fail to reject HD05.
Okay, so based on the test, we don't have convincing evidence.
Right, and this highlights something important. Failing to reject H201 doesn't prove HD is true. It just means we didn't find enough evidence against it.
Maybe the real effect is small and we needed a bigger sample size to detect it reliably.
That's a very common reason. Or maybe there really is no effect. We just can't be sure based on this data alone. Got it. Okay, that covers comparing proportions. What about comparing means, like average scores or average heights?
Right, let's shift gears to section 10.2, comparing two means. This is our tool when we want to compare the average value of some quantitative variable between two independent groups.
Independent groups, like comparing a random sample of men to a random sample of women.
Exactly. Or comparing outcomes for patients randomly assigned to treatment A versus patients randomly assigned to treatment B. The key is the individuals in one group have no connection to the individuals in the other.
And the statistic we focus on is the difference in sample means bar 1, bar 2.
Precisely. And just like with proportions, we need to understand its sampling distribution. What kind of differences, bar 1, bar 2, would we get if we repeated the sampling or the experiment many times?
Does it also follow a normal distribution?
It can. The sampling distribution of bar 1 bar is normal if both of the original population distributions are normal.
Okay, what if they aren't normal?
Then we rely on the central limit theorem. If both sample sizes, ANO1 and ANO2, are large enough, usually we say 30 all threes is a guideline, then the sampling distribution of the difference in means will be approximately normal, regardless of the original population shapes.
Ah, the CLT saves the day again. So normal if populations are normal, or approximately normal if samples are large. What about the center and spread?
The center, or mean, of this sampling distribution is just the true difference in population means, MEO by VNOA2.
Makes sense.
And the standard deviation of the difference depends on the population standard deviations. And the sample sizes, VNO1, 2, and 2. The formula is fraxpol 12 and 12 plus fraxpol and 12. Again, assuming the 10% condition holds if we're sampling.
Okay, but just like with proportions, we usually don't know the population standard deviation sigma dot to designate.
Exactly. That's the practical reality. So when we build confidence intervals or run significance tests, we have to estimate them using the sample standard deviations, 6 to 1 and 6 to R.
And when we use sample standard deviations instead of population standard deviations,
we have to use a Q distribution instead of the normal distribution. And our measure of variability becomes the standard error of the difference. SC bar 1 plus 12 1 plus frusfruxing.
Got it. So procedures for comparing means will involve T stuff, not Z stuff, because we're using SES1 over in step 2.
You got it. Let's talk confidence intervals for Teal Munt 22. The goal is to estimate the true difference between the population means.
Conditions first.
Always. Random data from two independent random samples or two groups in a randomized experiment. 10% condition if sampling without replacement. And the big one, normal large sample.
Okay, unpack that normal large sample condition for means.
This is crucial. The condition is met if either both population distributions are stated to be normal or both sample sizes, 21 and 2 are large, typically $2 off.
What if the populations aren't necessarily normal and the sample sizes are small, say 10 to $50 an hour?
Then you're in a trickier spot. If one $30 and the population shape is unknown, you must examine graphs of your sample data for each group separately. Look at dot plots, histograms, or box plots.
What are we looking for in those graphs?
You're looking for reasons to doubt that the underlying population could be reasonably normal. Specifically, check for strong skewness or the presence of outliers in your sample data. If you see those, using the two procedures isn't safe.
But if the sample graphs look roughly symmetric and have no outliers, even with small samples,
Then it's generally considered okay to proceed with the two procedures, assuming the populations themselves aren't drastically non-normal. You just need to state that you checked the graph.
okay, so conditions met. The formula for the confidence interval.
It's the familiar structure. Statistic bars, critical value, x, standard error. For two means, that's PSETSETSE bar 2 bars. We call this a two-sample, two-interval for a difference between two means.
And that critical value comes from the 2 distribution. But what about the degrees of freedom, DF? I remember this being weird for 2 samples.
Yes, the degrees of freedom for the two-sample procedures are calculated with a rather complicated formula. The good news...
Let the calculator handle it.
Exactly. Your calculator or statistical software will calculate the degrees of freedom using that complex formula, often called the Welch-Satterthwaite approximation. It usually results in a non-integer DF. Always use this value, it's the most accurate.
What if we have to do it by hand or the calculator isn't available?
There's a conservative, simpler option. Use the smaller of 1-1 or NA11 as your degrees of freedom. This is easier to calculate but results in a slightly wider, less precise interval, so always prefer the calculator's DF if possible.
Okay, always use technology's DF. Got
Yeah.
it. Example time. How about that apartment rent comparison?
Good one. A student samples 10 one-bedroom apartments and 10 two-bedroom apartments in a large city to compare mean rents. Let's say $1, $800 1BR, $6 in dollars, $700 2BR, $7 a right. Both $1 and $10.
Okay, conditions. Independent random samples. Assume yes. 10%. Assume rents in a large city is a huge population, so yes. Normal large sample.
Sample sizes are small. Lens $10 too. So we'd need to look at dot plots or box plots of the rents for the 1BR sample and the 2BR sample. Let's assume the problem states there's no strong skewness or outliers in either sample.
Okay, assume graphs look okay. Conditions met. Now calculated, say, 90% confidence interval for Bu1 plus Mulwin.
We use the formula, bar1 p-squared fraction. We plug in the means and standard deviations. We find the standard error. Then we need data for 90% confidence with the calculator's degrees of freedom.
And the calculator would give us the DF, maybe something like 17.8.
Exactly, something like that. We find the t-dollar for 90% confidence and DF 17.8 using NVT function. Let's say the final interval comes out to be -$144.80 and $11.20. Note, I use slightly different means than the book example here to get this result for illustration. Let's use the book data. That I got $174.888. The difference is $874.88 on $952.80, $952.84 sober. The difference is $874.08, $952.08, $944 and $11.20.
Managed at $144 and $80.80. How do we interpret this? Remember, it's me to one me.
Okay. We are 90% confident that the true mean monthly rent for one-bedroom apartments in this city is between $11.20 and $144.80 less than the true mean monthly rent for two-bedroom apartments.
And again, the key insight, does the interval contain 0?
It does not. Both endpoints are negative. Since zeros is not in the interval, we have convincing evidence at the alpha point n hence little level corresponding to 90% confidence that there is a real difference in mean rents between one and two bedroom apartments in this city. Specifically, two bedrooms cost more on average.
Makes sense. And the AP exam tip is probably similar.
Yep. Name the procedure. Two-sample t interval for you menu. Report the interval and definitely report the degrees of freedom your calculator gave you. Then interpret in context.
Okay. Now for significance tests. $H is usually ween Lori equals little dog.
Almost always, yes. Mu more in equals $dollars or $dollars. Mu more equals you. The alternative how specifies the direction of difference you're testing for, greater than, less than, or not equal.
Conditions are the same as for the interval. Random, 10%, normal large sample.
Correct. And the test statistic is a t-score. It's t-score, fract hypothesized difference.
As text hypothesized difference.
Jeffrey, port 1, BART 1, where 6 NSC bar 1 plus frac standard error.
Exactly. This is the two-sample t-test for a difference between two means.
And we find the p-value using the t's distribution with the same weird degrees of freedom from the calculator.
The very same DF. Use your calculator's TCDF function with the calculated t-score and degrees of freedom to find the p-value.
Let's try the longer work week example, comparing mean hours worked in 1975 versus 2014 using GSS data.
Okay. 1975, 1 BART 138.97, S1 13.13 tellers, 221.91, S2 14.1919, S2 14.355.
Let's test if the mean hours worked changed.
Hypotheses. Independent random samples assumed from GSS. 10% condition? Sure, population of U.S. workers is huge. Normal large sample.
Yes, both sample sizes, 764 and 1501, are way bigger than 30. So CLT applies. Conditions met.
Good. Now calculate the standard error using Shoes dollars N1, S282, and 202, then calculate the t-statistic. 280, $41.91, $38.97 Zimode SE-way.
Okay, the difference is about 2.94 hours. Plugging into the formulas, what does duo come out to?
The calculation yields approx $4.88.
Wow, that seems like a large t-score. Degrees of freedom. Calculator would give something probably large.
Yeah, with those sample sizes, the DF will be quite large, maybe around 1,800 or so.
So the p-value for $224.88 with many degrees of freedom in a two-sided test.
That's going to be tiny, right?
Extremely tiny. The calculator uses a p-value of approximately 0.000000115, like 1 in a million chance.
Okay. Conclusion. Comparing to alpha 0.0555.
Since the p-value basically zeros, much less than alpha 0.055, we reject $. So there is very strong convincing evidence of a statistically significant difference in the true mean number of hours worked per week by Americans between 1975 and 2014.
And the sample means suggest it increased.
Yes, the sample data suggests the average work week got longer. Okay, one last thing on two sample t-tests. You mentioned pooling for proportions tests. Is there pooling for t-tests?
Excellent question. Yes, some older methods and some software offer a pooled two-sample t-test. This procedure averages the two-sample variances, as 12 of 22 and 202 tests, if you are willing to assume that the population variances sigma 12.2 and sigma 2.22 are equal.
Assume equal population variances. Is that usually safe?
Generally, no. It's often not a realistic assumption. And importantly, the standard two-sample t-test, the one we just discussed that doesn't assume equal variances, works very well even when variances are different.
So the non-pool test is better?
It's more robust, yes. The pool test can give misleading results if the population variances aren't actually equal. So the strong advice for AP statistics is never use the pooled t-test or pooled t-interval for comparing two means unless you are specifically told to assume the population variances are equal, which is rare. Always use the standard unpooled procedures your calculator defaults to.
Got it. No pooling for means, unless forced to. Pooling okay for proportion tests because HEOTL over dollars assumes p-tilde 2 downs.
You've nailed the distinction.
All right, now for the last section, 10.3. Comparing two means again, but this time with paired data. What's that about?
This is where study design becomes absolutely critical. Paired data arises when our two sets of measurements are not independent. They come in pairs.
Pairs. Like how?
Two main ways. First, you might have two measurements on the same individual. Think before score and after score on a test, or measuring the flexibility of someone's left arm versus their right arm.
Okay, same person, two measurements. What's the other way?
The second way is when you have two distinct but very similar individuals that have been intentionally matched up based on certain characteristics, and then one member of the pair gets treatment A, the other gets treatment B, like using identical twins in a study, or matching two patients based on age and health status, or using two adjacent plots of land in an agricultural experiment.
So the goal is to compare the two treatments or conditions, but using these related pairs.
Exactly. And the key idea for analyzing paired data is brilliantly simple yet powerful.
What is it?
You don't analyze the two original lists of data separately. Instead, you first calculate the difference within each pair.
Like after minus before, or twin A minus twin B.
Precisely. For every single pair, you compute one difference value. This transforms your two lists of data into a single list of differences.
Ah. And then what do you do with that list of differences?
You analyze that single list of differences using the methods we already know for a single sample mean. Specifically, you use a one-sample t-interval or a one-sample t-test on the differences.
So paired data analysis is just one sample t procedures applied to the differences.
That's the secret. It simplifies everything.
Why is this better than just treating them as two independent samples?
Because pairing often reduces variability. Think about the identical twins IQ example. Twins share genetics and often early environments. Their IQs are likely to be more similar to each other than to randomly selected individuals.
Yeah.
If you just compared the group of high-income twins to the group of low-income twins using a two-sample t-test, the natural variation between different pairs of twins might obscure the effect of income. You'd see lots of overlap.
Okay.
But if you calculate the difference in IQ for each pair, high-income twin IQ, low-income twin IQ, you effectively cancel out the shared genetic and background factors unique to that pair.
You're isolating the effective income within each pair.
Exactly. And when you look at the distribution of those differences, the effective income becomes much clearer. You might see almost all the differences are positive, even if the original IQ scores overlapped a lot. It increases the power of your analysis to detect a real difference if one exists.
Wow, that's clever.
Yeah.
Turn a two-group problem into a one-group problem on the differences.
It's a very common and powerful experimental design technique.
Okay, so if we're doing a confidence interval for the true mean difference, which we often call median, we're essentially doing a one-sample t interval on that list of differences.
So the conditions must be for the differences,
Yeah.
right? Absolutely. Condition 1, random. The pairs themselves should be randomly selected, or if it's an experiment, treatments should be randomly assigned within pairs, or the order randomized, like in the caffeine study. Condition 2, 10% condition applies if you're sampling pairs without replacement. Check if the number of pairs is less than 10% of the population of pairs. Condition 3, normal large sample for the differences.
So the distribution of the differences needs to be approximately normal, or the number of pairs needs to be large.
Correct. And if NERV is small, you need to make a plot, dot plot, histogram box plot of the differences and check for strong skewness or outliers in that plot.
Makes sense. Check the differences and the formula for the interval.
It's just the one sample t interval formula applied to the differences. Where SCOT is the mean of the differences, DIVS is the standard deviation of the differences, and debye is the number of pairs.
Yep. And the degrees of freedom for $t is simply Nerville 1. Much easier than the two-sample case. Definitely. We call this a paired two interval, or a one-sample t interval for a mean difference,
Both names are common.
and for significance tests for mood.
Same idea. It's just a one sample t-test performed on the list of differences.
Hypotheses are about the mean difference. Velo, dollars yellow, and half little b $7 or $.
Correct. Conditions are the same as for the paired t interval. Check randomness of pairs assignment, 10% if needed, normal large for differences.
And the test statistic.
It's the one sample t statistic for the differences. T-SCORT stretch n out to cell.
Okay. Find the p-value using the t distribution with t indiced to later.
Exactly. Let's look at that caffeine dependence experiment. 11 volunteers measured depression score after placebo and after caffeine, order randomized. They calculated the difference. Placebo score, caffeine score.
They expect withdrawal, placebo, to increase depression, so they expect this difference to be positive. Mutative, huh?
Right. Sample size is $111 which is small. So they'd need to check a plot of the 11 differences. Let's assume it showed no strong skewness or outliers. Random assignment of order was done, so conditions are met.
The sample data showed a mean difference diff 7.364 Hz and standard deviation of differences 6.9188x.
Okay. Now calculate the t statistic. TT 7.364 cents and SIC is approx 3.533.
Now we need the p-value. It's a one-sided test, so we find the area to the right of $3.533 in a t distribution with df1 back 4-1 equivalent 10.
Okay, TCDF 3.53, infinity 10.
What does that give?
The p-value is approximately 0.00027.
It's a trainee p-value compared to alpha 0.00c7 powers of stars.
Since p-value 0.0007 Hoffa, Booksever 747, we reject $.
Conclusion.
We have convincing evidence that the true mean difference in depression score, placebo caffeine, is greater than 0. In other words, caffeine deprivation increases depression scores for caffeine-dependent individuals like these volunteers.
And because it was a randomized experiment.
We can actually conclude causation. The caffeine deprivation caused the increase in depression scores. That's the power of randomization in experiments.
Great example. Okay,
Yeah.
This distinction seems really important. How do we know when to use paired procedures versus the two-sample procedures from section 10.2? This sounds like a classic AP question.
It absolutely is. It's one of the most common points of confusion. Your choice of inference procedure, paired T or two-sample T, depends entirely on how the data were collected, on the study design.
So lay it out for us. When do we use two-sample T procedures?
Use two-sample T procedures when your data come from two independent groups. This means 1. Two separate independent random samples were taken. Example, a random sample of boys and a separate random sample of girls. 2. Or, in an experiment, individuals were randomly assigned to one of two different treatment groups. Example, treatment A or treatment B, but not both. This is called a completely randomized design.
A key hint here. If the two groups have different sample sizes, it must be two independent samples. It cannot be paired.
Excellent point. If $1 and 1022, it's automatically a two-sample situation.
Okay. And when do we use pair T procedures?
Use paired T procedures when the data are collected in pairs. This means 1. You have two measurements on the same individual, before, after, left, right, condition 1, condition 2. 2. Or you have measurements on two individuals who were deliberately matched based on relevant characteristics before the experiment began. Twins, matched patients, matched plots.
The essence is that the two measurements within a pair are related or linked somehow. They're not independent.
Precisely. And you analyze the differences within those pairs.
Let's test this with that "are you all wet" scenario. Scuba fins. Each diver tests both types of fins, paired or two-sample.
Each diver provides two measurements. That's paired data. Analyze the differences in time for each diver. Paired t-test.
Okay. Piranha fish lengths. Comparing lengths from a sample caught then versus an independent sample caught now.
Two independent samples from different time periods. Two-sample t-test.
Wetsuit and shark bites. Two groups of identical drums. One group gets wetsuits, the other doesn't. Randomly assigned. Bites measured.
Two distinct groups of drums. Random assignment to group. That sounds like a completely randomized design. Two-sample two-test.
Oh.
Even though the drums are identical, they aren't paired in the sense of one drum getting both treatments.
Got it. The design dictates the analysis.
Always. And let's quickly revisit that get your heart beating activity to really drive home why paired designs are often preferred if possible.
Right. The pulse rate example. If we did a completely randomized design, randomly assign some students to stand, others to sit, and compare the group's pulse rates.
The natural variation in resting pulse rates between different people is huge. Some people just have higher pulse rates than others. This noise makes it hard to see the signal, the effect of standing. You might get a p-value around 0.09 and fail to find significant evidence.
But if we use a matched pairs design, where each student measures their pulse, both sitting and standing,
and then we calculate the difference, standing pulse, sitting pulse, for each student,
we cancel out that person-to-person baseline variability. Now we're just looking at how much each individual's pulse changed.
Exactly. The variability in the differences will be much, much smaller. And when you run a paired test on those differences, you'll likely get a p-value very close to 0.
So the pair design was much more powerful. It was better able to detect the real effect of standing on pulse rate because it controlled for individual variation.
That's the aha moment. By reducing variability, paired designs often give you more statistical power.
Fantastic summary. Okay, let's try to wrap this all up. Today, we've really taken a deep dive into comparing two groups. We navigated the different methods for proportions, for independent means, and for paired means.
Yeah, we covered how to think about sampling distributions, how to build and interpret confidence intervals, and how to perform significance tests for each scenario. And crucially, how to check those conditions.
Right. The conditions are key for validity.
If we connect this to the bigger picture, these methods aren't just abstract formulas. They're about making informed decisions from data. It's about separating a real effect from random chance.
Like deciding if a new drug actually works better than a placebo, or if one teaching method is genuinely more effective, or even if seeing tattoos influences survey answers.
It gives you the tools to challenge claims and interpret research critically. So this raises a question for you, the listener. Now that you have these powerful tools for comparison, what two things are you curious about comparing in the world around you? What difference would you want to investigate?
That's a great thought to leave people with. We really hope this deep dive has brought some clarity and confidence for your AP Statistics journey as you tackle Chapter 10.
Thanks for tuning in.
Thank you for joining us on this deep dive. This has been a last-minute lecture production.